Is it visible to everybody?
Yes, ma'am.
Yes.
Okay. So we have started with this numerical example and you have noted down this problem statement in the last lecture, and also you have drawn this diagram. Okay. So let us start the design. What we are supposed to design? The beam ABCD. Okay. This is three span continuous beam, which consists of the first span of AB of 3 meter, BC is of 5 meter, and CD is of 4 meter. Okay, so this is the three span continuous beam which we have to design for this problem. Okay, so let us start with the first step. What is the first step? Guys, what is the
Size of
first step? Yes. Yes. Somebody?
deciding the size of the beam.
Yes, deciding size of the beam. So let us decide the size of the beam first. Size of beam. So first we decide the width of the beam, right? What is the minimum and maximum value for width of the beam? Students,
200 mm is width of minimum, or it is the width of the wall, which is given as 150 mm, width of brick masonry.
150 mm. Okay. 200 or 150 mm, whichever is greater. Am I right?
Yes, ma'am.
So 200 is greater, and the maximum width is width of the supporting column. What is the value given?
300 mm.
300. Okay. So within 200 to 300, we have to decide the width. Now, in earlier all problems, we have decided we have directly taken the width of the beam as the width of the supporting column. Okay. Here, what I'm going to do, I will try to make the design little economical, and I will consider the value between 200 and 300. So normally the external wall widths are 230 mm, though it is mentioned here the width of brick masonry as 150. We will consider 230 as the width of the beam. Okay, so I'm assuming here the value of the width of the beam as 230 mm. Okay, then we have to decide the depth of the beam also. Second step, how to decide the depth?
Clear span divided by 10 to clear span divided by 16.
Okay, so clear span. Now if I will go back to the diagram here, in this diagram there are three spans. Okay, AB has 3 meter length, BC has 5 meter, and CD has 4 meter. So out of the three spans, I will consider the largest one, that is 5 meter span, and for that I will decide the depth. Okay, so span by, anybody asking permission? No. Okay, so span by 10, right? Depth is decided as students.
Clear span
Span
by
by
10.
span by 16.
Okay, so clear span by 10, 5000 by 10 to 5000 by 16. Tell me the values.
मॅम तुमची स्क्रीन ब्लर दिसते.
दिसतंय का व्यवस्थित आता?
हो मॅम.
हो
Yes,
मॅम
ma'am.
आता ते- yes.
ओके, चला सांगा व्हॅल्यू पटपट.
500 to 312.5 mm.
500 to 312, set with 13. I will consider 313. Okay, so let us adopt the largest value. So adopt D is equal to 500 mm. Okay, we'll consider effective cover as 50 mm. So the effective depth D will be equal to 500 minus 50, 450 mm. Okay. Now, all of you open IS 456. Again, today I forgot to keep it open. So I will open it first in my laptop and I will share it again. Meanwhile, all of you open IS 456. We want the formula for the flange width. Okay, last time we have discussed about it. Last time means when we started the design of flange beam, that is T-beam, we have already discussed about this. But today again, we will require the same concept here. So I just want everybody to open your IS 456 and we will see how to consider the flange width. Can anybody tell me the page number where you can find out the flange width values for beam? Let me check how much do you remember. Students, I think you are not in a mood of learning today, huh?
Page number 37.
Yes, page number 37, correct. So I will present my screen again and I will show you that page number. Is this visible to everybody? Students?
Yes, ma'am.
Huh. Okay. Now, two different formulas you can find out here. For T-beam, the width of the flange is given, and for L-beam, the width of the flange, the different formula is given. Why I'm showing all this? Because if you consider or if you go back to our diagram, this is our diagram, right? So in this diagram, in earlier problem, we designed a intermediate beam, which was like a T-beam. Now here we want to design the side beam, which is ABCD, a continuous beam on the top. Now we are observing plan, that's why I'm using the word top and bottom. Okay, so on the top of ABCD, this line, there is nothing. Okay, and at the bottom side there are the slabs, or in other words I can say that ABCD is a continuous beam. On its left hand side there is nothing, and on the right hand side there are slabs. So beam ABCD is like a L beam. It is a side beam. So it will behave like a L beam and not like a T beam. Okay, we have calculated, we have decided the width B, which is actually the width of the web. Now here it is, again, we have to consider that continuous beam ABCD, as it is a L beam, certain portion of the flange of the beam or certain portion from the slab will behave like a part of the beam, which will comprise on which will make or which will form the flange of the beam. So if I will go back to the this diagram, you can see here diagram A. This is like this is a column, and at this location our beam is there, and this is the slab. So some portion of the slab will participate in resisting the moment along with the beam, which will form a part of the flange of the beam. Okay, so that flange width is calculated by using the second formula now, which is used for L beam. That is BF equal to L0 upon 12 plus BW plus 3 times DF. Okay, so this formula we have to make use here to find out the depth of the width of the flange. Okay, so I will go back to the write up here and let us write down now. We have decided the width of the beam Now this width of the beam is actually at the bottom. So I will write down it as BW. Okay. And now we have to find out the width of the flange. Okay. So I will just write down here for flanged beam. For flanged beam, I will just write down here beam ABCD is continuous L beam. This is very tedious, huh? While writing in Word. Okay. Beam ABCD is continuous L beam. Okay. So for that, you just write down the BF value, that is width of flange, BF. The formula is L0 upon 12 plus BW plus 3 times BF. Okay. What is L0 now? Let us move to the IS code again. What is L0? L0 is the distance between points of zero moments in the beam. L0 is the distance between points of zero moment in the beam. How will you consider this now? L0. Now L0 in case of continuous beam, we will consider as, if I will go back to this diagram here, this end is actually a simply supported and this is the fixed beam, okay, or fixed support, considered as fixed support because the beam is continuous over the next span. Similarly, C is considered as a fixed support and D is again considered as a simple beam, okay, or simple support. So if we consider AB span, BC span or CD span, um, uh, on every span there is a UDL. So the load acting from the slab, load acting from the wall and the self weight of the beam, all three will form the total load acting on a beam, and that load is actually the UDL. So the L0 value, if I will go back to the code here, L0 is the distance between points of zero moments in the beam, and that is taken as 0.7 times the length L. Now here the length we have to consider is the least one. So there are three spans. I will consider all the three spans. Um, Out of the three spans, the least one is 3 meters. So I will consider that value here. So L0 is taken as 0.7, the least span, that is 3 meters. So what is the value? It is 2.10 meters. Okay. And what is DF? DF is the depth of the flange. So the slab which is taking part in making the flange portion of the beam, its depth we have to consider. So what is the depth of the slab? It must be given in the problem statement. So just look into the problem statement and tell me the value.
120 mm.
120 mm.
120 mm. Okay. So it is 0.12 here. Or let us consider the value in the millimeter directly and put the values here and tell me what is BF you are getting. Okay. So BF will be, this value is 210. Am I right? Or 2100. Sorry. So L0 is 2100 divided by 12 plus BW we have taken as 230, right? Plus 3 times 120. So tell me BF value.
765.
Yes, it is 765 mm. Okay, so this is the width of the flange. Now we have to find out the effective span also. So I will just write down the effective span. effective span, for each span we have to calculate separately because the values are different. Okay, so I will go back again to the code and we'll see the clause for finding the effective span. Okay, so quickly tell me what is the page number. Yes, this is a page number, page number 35. Okay, here, effective span. For continuous beam, in case of continuous beam or slab, if the width of the support is less than 1/12 of the clear span, the effective span shall be taken as in 22.2a. If the supports are wider than 1/12 of the clear span or 600 mm, whichever is less, the effective span shall be taken as under. For end span with one end fixed and the other continuous, or for intermediate span, the effective span shall be taken as clear span between supports. For end span with one end free and the other continuous, the effective span shall be equal to the clear span plus half the effective depth of the beam or slab, or the clear span plus half the width of the discontinuous support, whichever is less. And in case of spans with roller or rocket bearings, the effective span shall always be the distance between the centers of bearings. Now, if you consider our case, first of all, find out what is L by 12. L by 12 of the clear span. What is that value? Or 1/12 of clear span. If you consider the first span AB, the span is 3 meters. So 3 by 12, the value is 0.25. And if the width of the support is less than this value, so what is the width of the support? It is 300 mm, right? So 300 mm, and this value we are getting as 2500. So I will, or simply I will find out in mm, 250. So width of support is greater than L by 12. Okay, if the width of the supports are wider than this, the effective span shall be taken as under. So we have to consider these three criteria. Out of these three, the appropriate criteria we have to select. Okay, so for first span, we have checked this. Let us move to the second span. 5000 divided by 12. The value is 416 and the width of support is 300. So that value is coming less. Okay, so for that we have to refer 22.2a clause. And for third span, again the span is 4 meters. So 4000 divided by 12, the value is 333 and the width of the support is 300. So again we have to refer the first case. Now, what are the support condition? For the first span, that is for span AB, all the supports are our simple supports. We have considered all supports as simple support. So the condition is third condition. In case of spans with roller or rocket bearings, the effective span shall always be the distance between centers of bearing. It means center to center distance between the supports is our effective span for span AB. Now, for other two spans, as these three criteria are not applicable, the 22.2a criteria is applicable. That is, whatever is the criteria which we have used for simply supported beam, same we have to use. So, what is the criteria? Clear span plus effective depth of the slab or center to center of the support, whichever is less. So, what is the clear span plus effective depth? Clear span for 5 meter, clear span is 5 meter plus effective depth of the slab or beam. Effective depth is 450, right? So 5000 plus 450, 5450, and
Ma'am,
center to center. Yes.
ma'am, for the second part, that is part BC, the
Hmm.
Li 12 is coming as 416, which is greater than the width of the support. Width of support
Right.
is 300.
Right. So for that, tell me
So
again.
we for that we use the first point for the end span with one end fixed.
No, one end fixed and other is continuous. Now our both ends are, if you come, or if I will draw the diagram here, let me draw the diagram of a beam. That is considered like this. The diagram of a beam is like this. We are considering all the support as simple supports. Okay. All the supports as simple supports. So this is not fixed. one end is fixed and another is continuous. So this end must be fixed and this is continuous. Then your second case will be applicable. This case. Okay, so in our case, what we are considering, all the ends are supported with simple support. So the third case will be applicable in that case. Is it clear to you now?
Yes, ma'am.
Okay. So in short, for the two spans, that is for span BC and CD, the third case is there, center to center. And if you consider the first span, for first span, clear span plus effective depth or center to center of the support, whichever is less. So obviously the second case will come less, that is the center to center distance between the support. So for all the three spans, we are getting now the same criteria, that is the center to center distance between the support is to be considered as the effective span. And now, if you consider this diagram, this is actually a center line plan. If I'll go back to the problem description here, this is the center line plan. So whatever the distance is given here are the center to center distances directly. Okay. So write down now the effective span for all the spans. You just write down for all spans. L effective is taken as L center to center. Okay. So I will write down here for span AB, L effective is 3 meters. For span BC, L effective is 5 meter, and for span CD, L effective is 4 meters. Okay. Is it clear to everybody?
Yes, ma'am.
Students? Okay. So what is the next step now? What is the next step?
Load estimation.
Yes, load estimation or load calculations. As discussed earlier, the load coming on the beam will be from three ways. One is from the column, from the slab. Second is from the wall above the beam, and third is the self weight of the beam. Okay, so let us come to the diagram now. Diagram of this slabs or the beam. Okay, this is the diagram, and you can consider, you can see here S1, S2, S3. First of all, observe their dimension. Let us consider the first slab, that is S1. The longer side is of 4 meter here, and the shorter side is 3 meter. Okay, so Ly is 4 meter here and Lx is 3 meter. Find out Ly by Lx ratio. Find out Ly by Lx. Guys.
1.33.
1.33. So the ratio is coming less than 2. So the first slab, S1 slab, is two-way slab. Okay, we have to identify first what is the type of the slab, and then only we can consider the load distribution, how the load is transferred from slab to the beams. Okay, so S1 is two-way slab. Similarly, if you consider S2 slab, in S2 slab the longer length is 5 meter and shorter length is 4 meter. So Ly is this side. So again Ly by Lx, find out the value. It is also coming less than 2.
1.2.
So, yes. So S2 slab is also a two-way slab. Come to the third slab. Now both the dimensions Lx and Ly are equal. The ratio is exactly coming equal to 1. So it is again less than 2. So S3 slab is also two-way slab. All the three slabs are two-way slab. Now in case of two-way slab, how the load is transferred? You can see this diagram. Okay. In this diagram, the load coming or transferred on the shorter beam or shorter side will be in a triangular form, and the load transfer on the longer side is in the trapezoidal shape. Okay, and considering these both these shapes, the formulae we have already discussed in earlier lecture, that the load coming on Lx will be calculated as WLx by 4, and on the longer beam Ly, it is calculated as W into Lx by 4 into bracket 1 minus 1 upon beta, where beta is the ratio of longer to shorter span of the beam. Okay, now let us come back to our diagram of the slabs, and now consider how the loads will be transferred. For the first slab S1, for the longer side, the triangular portion area we have to consider, from which the load will be transferred to beam AB. For the slab S2, the longer side is 5 meter, that is BC span, and on this longer side the load will be transferred into in the form of a trapezium or trapezoidal area. And for the third slab, that is S3 slab, as it is both the sides are equal, the distribution line, if you consider, it is simply, these are simply crossing to each other, and all the four beams, if we consider the triangular portion of the slab, we have to consider from which the load will transfer to the beams. Okay, so for CD span of the beam, from S3 slab, this triangular portion load we have to consider, which will be transferred on CD span. Is it clear to everybody? Students? Okay,
Yes, ma'am.
so for AB span, we have to first calculate all the loads. We will consider the spans of the entire continuous beam one by one. We will calculate all the ways, or from possible ways from which the load will be acting on span B. So we will first calculate the load distribution for span B, then AB, then we will go to BC, and then we will move to CD. Okay, so let us find out now first the loads acting on span AB. Okay, so let us consider here span AB. So for span AB, we have to first calculate the load acting on the slab. Okay, load from the slab. So we denote it as WS. How to calculate this now? Load acting on a slab.
Self weight plus floor finish
Self weight
plus waterproofing plus live load.
plus live.
Self weight plus waterproofing load plus
Floor finish and live load.
Live load.
okay.
Live load.
Okay. How to find out self weight?
25 times D, depth of the slab.
Yes. So I will denote it as DS, depth of the slab. Plus waterproofing load is not given, so no need to consider that. Second is floor finish. Is it given?
1 kilonewton per meter square.
Yes, 4 feet. And third is the live load. So let us calculate first WS. Okay. So WS will be equal to 25 into depth of the beam. I will calculate it in kilonewton meter. So it is 0.12, right? Plus floor finish is 1, right?
1.
And live load is
3.
3. So find out the load acting on the slab.
Seven kilonewton per meter square.
7 kilonewton per meter square. Okay. Now, from the slab S1, what is the load acting on the span AB? That we have to calculate. So from S1, I will go back to this diagram. From S1, the triangular portion we have to consider. And for triangular portion, the formula is, see, for shorter span, the formula is WS into LX by 4. So I will simply write down here the formula as WS into Lx by 4. Now Ws is 7 into Lx. Lx is the shorter span. So what is the shorter span here? 3 meter. So I will write down 3 divided by 4. Tell me the value.
5.25.
Kilonewton per meter unit. Okay. Then this is a load coming from the slab. Then here I will write down some marking over here. This is from slab. Now from wall we have to find out, right? So from wall, what is the formula?
Gamma W into TW into HW.
Yes. Gamma W for brickwork, the unit weight is taken as 20 kilonewton per meter cube multiplied by thickness. What is the thickness? Thickness of wall is given in the problem
150
statement.
150 mm.
150 mm. So it is 0.15 into height. Height. Floor to floor height must be given
3 minus 0.12.
3 minus 0.12. Why?
0.5, ma'am.
It should be the depth of the beam and not the depth of the slab. Okay, we are designing beam here. So we have to deduct the depth of the beam, which is 0.5. 500 mm is the depth of the beam. Overall depth we have considered, right? Am I right, Ritik? Ritik was talking, right?
No, ma'am. I was talking Omkar.
Omkar. Okay. I'm trying to identify your voices now. Okay, tell me the value now. What is the load coming from wall?
75 kilonewton per meter.
75 kilonewton per meter. All right. And the third is the self weight of the beam, which is
Ma'am,
calculated.
7.5.
Yes.
7.5.
7.5 or 75?
7.5. 7.5.
7.5.
7.5.
Okay. All right. Find out the self weight of the beam, which is calculated as 25 into B into D. Okay, so D is taken as D minus DF only. That is the depth of the web portion is considered only for self weight of the beam. Because weight of the slab we have already considered here. Self weight of the slab we have already considered here as 25 into ds. So that we have to deduct. That's why we have considered only the depth of the web from the beam. So put the values and tell me the value quickly. Depth of the flange means depth of the slab. Okay. df is nothing but ds only. So I will write down
2.185.
ds here. That is better. Yes.
2.185.
2.185 kilonewton per meter. Okay. So what is the total load? Find out total load. I will consider this as
14.
WAB. Yes.
14.935 kilonewton per meter.
14.935 kilonewton per meter. This is the working load. We have to find out the design load. Okay. So WAB design load will be this value multiplied by 1.5. That is 14.935 multiplied by 1.5 is the partial safety factor. What is the value?
$22.4025.
22.4025, 403. kilonewton per meter. Let us assume WAB as, I will round it off to the higher value, say 23 kilonewton per meter. And I have increased the load little bit, which is 23 kilonewton per meter. Okay, so this is the load we have calculated for span AB. Similarly, we have to calculate the load for span BC as well as CD. So let us do it quickly. The load coming on the this load WS will not change, right? This will remain constant. So we will directly move to this formula from slab, from wall, and the self weight. So the load coming from wall will also not change for the span BC or CD. This will remain constant. Self weight of the beam, this will also not change. Am I right? Self weight, because the depth of the beam and the width of the beam and the depth of the slab over or all the three slabs is same. So self weight of the beam will remain as it is. Only the load coming from slab will change. So we will quickly go to the span BC now for load calculation. So let us consider span BC. So I will write down the load from slab. Now here the slab is S2 slab. So again I will go to the diagram here. The slab load will get distributed in the form of a trapezium. So we have to make use of this formula. What is that formula? This formula, WS into LX by 4 into bracket 1 minus 1 upon beta. Okay, so let us write down this formula here. WS into LX by 4 into bracket 1 minus 1 upon beta. Okay, so let us first find out what is beta. For this, beta is Ly by Lx, right? So Ly by Lx, Ly, longer length. Longer length is 5 meter, shorter length is 4 meter. So 5 by 4. Tell me the value.
0.8.
0.8. Okay.
1.25.
What is this? 1.25?
Yes, ma'am. 5 by 4.
5 by 4. Okay. One point
25.
25. Okay. Now put these values here in the formula. WS we already have calculated. LX take 4 and find out, put the value of beta and find out the load coming from slab S2.
1.4.
Check it again.
I'm 1.4.
1.4. Correct है ना?
Yes,
Ma'am,
ma'am.
1.75.
WS काय घेतलं value? What is WS you have taken? It is 7, right?
7. Yes, ma'am.
Okay, so I will write down better. I will write down 7 into 4 by 4 into bracket 1 minus 1 upon 1.25. This value is coming as
1.4.
1.4 kilonewton per meter. Okay, this is a load from S2 slab. Now the load from wall, it is same as per the earlier. Tell me the value quickly.
7.5.
And self weight will also remain same. The value is
2.18.
2.15.
2.18. 185. Find out total load. So this is W.
11.085.
Yes.
11
Again.
point 11.085.
Find out the design load.
16.628.
16.628. Let us consider it as 17 kilonewton per meter. Okay. And this should be smaller because it is UDL. Now similarly find out for span CD. You directly tell me the total load now. Span CD. All of you do the calculation. Now, how to consider the load from the slab? From slab S3, the triangular load you have to consider. So it is W. The formula is WLX by 4. That formula you have to use and find out the load. So tell me the value quickly.
16.685.
Tell me the ultimate load.
25.03.
This is WUAB. Sorry, I forgot to write down the sign for ultimate. WUCD. Yes. What is the value?
25.03.
Okay. So I will consider this as 25. All right. So let us draw now a diagram for a beam showing the loads and spans. So this is beam ABCD, A, B, C, and D. Okay. And show the UDL on each span. What is the UDL on first span? The value? It
23.
is 23 kilonewton per meter. Then second span, tell me the UDL.
17.
17 kilonewton per meter. And third span,
25.
25 kilonewton per meter. Okay. AB span is of 3 meter. BC is 5 meter. And CD is 4 meter. Okay, this is just the first or second step we have completed, that we have calculated the load acting on a beam. Now the next step to find out the moments. Okay, the maximum moment and maximum shear force acting on a beam. Now this is a continuous beam, and for continuous beam we have to make use of some analysis methods to find out the moment and the shear forces. So for continuous beam I will go with moment distribution method to find out the moments and the shear forces. Okay, so do you remember this method? Can anybody quickly tell me how to apply this method to find out the moments? Guys? Nobody remembers this? Students. Okay, so shall I discuss the method, or should I write down directly the values and you will do it as a homework? अरे कुणीच बोलत नाहीये, मला कसं कळणार आहे? ओंकार.
मैम डिस्कस कर.
ओके. पण काहीच आठवत नाहीये तुम्हाला मोमेंट डिस्ट्रीब्युशन मेथड.
Ma'am, ma'am,
हा. व्हॉट इज द फर्स्ट स्टेप?
to calculate fixed end moments, first step, and second one
Correct.
is to calculate distribution factors, and third one is we need to consider the distribution factors and moments that in a table form.
मोमेंट डिस्ट्रीब्युशन टेबल.
Table.
हा. तर टेबल प्रिपेअर करायचं. फाईन. लेट अस स्टार्ट वन बाय वन नाव. लेट अस फाइंड आउट फर्स्ट the fixed end moment. Fixed end moments. Okay. We will consider the first one, that is for span AB. I will write down the fixed end moment as MFAB. How to calculate it? The fixed end moment, it is considered as
Minus WL square by 12.
correct, minus WL square by 12, because the UDL is acting on this span. And I think minus means you have considered here the moment is acting in this fashion. So anti-clockwise moment you have taken negative, and clockwise moment you have taken positive. So simply this is minus WL square by 12. So put the values. W is 23, L is 3. So 23 into 3 square by 12. What is the value?
17.25.
17 point. Voice is very slow, low. Voice coming is very low. Kilonewton per meter square. Okay. Now the next is MFBA, right? Am I right? MFBA.
Yes, ma'am.
The value will be the same because the span is the same one here. So it will be simply plus WL square by 12. The value is same. So I will directly write down the value as plus 17.25 kilonewton per meter square. Similarly, now next we have to find out for span BC and then CD. So for span BC, I will write down MFBC. MFBC. Again, it is minus WL square by 12. W value is 17. L is 5. Put the value and tell me the value quickly.
$35.416.
Tell me again, your voice is breaking.
35.416.
42. Okay. 35.42 kilonewton per meter square. Similarly, MFCB, the value will be positive only because it is for the same span. Okay. Then let us come to the third span, that is CD. The load is 25 and span is 4 meter. So MFCD, again it will be minus WL square by 12. So put the values and tell me. All the spans are subjected to UDL. So the formula of fixed end moment will remain same.
Ma'am, moment म्हणल्यावरती युनिट किलोन्यूटन पर मीटर येणार ना, किलोन्यूटन मीटर.
Oh, sorry. Correct. किलोन्यूटन पर मीटर. हे मी खोडते बरं का आता, कारण हे इरेज करायचं म्हणजे मोठाच. ट्राय. Yes. Tell me the value now for MFCD.
33.33.
33.33 kilonewton meter. Kilonewton per meter square नाही. kilonewton meter. इकडचं पण चुकलंय सगळं. So this is kilonewton meter. Okay. And similarly, MFDC will be plus 33.33 kilonewton meter. Okay. So we have completed the first step, that is finding the fixed end moment. Now the second step is considering the distribution factor. So I will name it simply as distribution factor table. Okay, distribution factor table. Because we have to consider the member stiffnesses also, we have to consider the various joints, various members, and for each joint and member, we will write down the distribution factor. So for this beam, now we have to consider the joint where there are two or more than two members connected. Okay, so for joint A, there is only one member, so we don't consider joint A. Go to joint B now, there are two members B and BC, so we have to consider joint B. Similarly, next at joint C, there are two members CB and CD, so joint C is to be considered. And at joint D, only one member is there, DC, so joint D is also not considered. So there are two joints now, and considering four members. So I will simply write down first the table here, distribution table. So first I have to write down the joints. Then I will write down members. Okay. Then I have to write down the member stiffness factor. Okay. Member stiffness factor, which is denoted as K. Right? K. And then next is joint stiffness factor. Joint stiffness factor, which is nothing but summation K. Okay, this is summation K. And next is distribution factor, which is calculated as K divided by summation K. Okay, so let us consider now one by one the joints. The first joint is joint B. And what are the members associated with this? BA and BC. Okay, so members are BA and BC. Okay, what is the member stiffness factor? How it is calculated? Do you remember anything?
4 EI by L.
Okay, when it is considered 4 EI by L and when to consider 3 EI by L? Yes, so to find out the member stiffness factor for this joint B and for BA member, we have to consider the support condition of the farthest support, okay, or the far end, support condition of the far end. If the support condition at the far end is fixed, if this end, now for BA member, the far end is A, if A is having a fixed support, then the K formula will be 4 EI upon L. And if the far end support is of hinged or roller support, in this case, the value of K will be 3 EI by L. Now, in our case, BA span, for BA span, A is the far end, and for this end, the support is a simple support. It is not fixed support. So, the K factor will be 3 EI by L. Okay. Now, for BA, let us write down this member stiffness factor, so which is 3 EI by L. Okay, so EI is a constant, so I will simply ignore this, because when we'll move ahead for finding the distribution factor, the EI from summation K and K will get cancelled. So I will simply write down 3 by L here. So this is 3 by, what is the L value for span AB? It is 3 meter again. So 3 by 3 is coming equal to 1. K is coming equal to 1 for BA. Now coming to the second member, that is BC. For BC, C is the far end, and here the beam is continuous over the support C. Okay, so when a beam is continuous over the support, this is considered as an intermediate support, and intermediate support is always treated as a fixed end. Okay, so in case of member BC, far end C is supported with a fixed end because it is an intermediate support of a continuous beam. So for this case, for BC span, the K formula will be 4 EI by L. So this is 4 EI by L. Okay, so 4 upon L. What is L for BC? It is 5 meter. Okay, so it is 4 by 5. What is the value?
0.8.
0.8. Okay. All right. Now the joint stiffness factor summation K is calculated as summation of these two. So what is the summation? It is 1.8. So find out the distribution factor for member BA. It is K upon summation K. So it is 1 upon 1.8. The value is
0.55.
0.55. Similarly, for BC, it is 0.8 divided by 1.8. So the value is
0.44.
0.45.
0.45. Okay. Okay, this is for joint B. Similarly, there is one more joint, that is joint C. So let us find out the same thing for joint C. The values, the lines I will draw here again. So for joint C, there are two members, CB and CD. CB, let us come to the member CB. Again for CB, B end is a far end and it is an intermediate support. So this will be treated as a fixed. So for CB, the formula for member stiffness K will be equal to 4 EI by L. Okay, so this is 4 by what is L? Span CB is 5 meter. So 4 by 5, it is 0.8 again. And for CD, coming to the span CD here, D is a far end support and it has a simple support. So the formula for stiffness, member stiffness will be 3 EI by L for CD. So for CD, this is 3 EI by L. So this is 3 by 5. 5 or okay.
3 by 4.
4. 3 by 4.
0.75.
0.75.
Yes. Point 75, right?
Yes, ma'am.
Now find out joint stiffness factor, that is summation K. What is the summation?
1.55.
1.55. 0.8 plus 0.75. And find out now the distribution factor. So it is K upon summation K. So it is 0.8 upon 1.55. This is for
0.5.
0.52
0.52.
and 0.4.
Okay, this is 0.75 by 1.55. So 0.48.
48.
Okay. So here we got the distribution factors now for our beam. So we will draw the diagram of the beam, or instead of writing the diagram, drawing the diagram, I will go to the table now. Okay. So the third step, I will write down now here the moment distribution table. Okay. So here I have to write down the joints first. Then I will write down members. Then I will write down distribution factors, and finally the fixed end moments. Okay, so first joint is joint A, then joint B, C, and D. For A, the member is AB. For B, there are two members. So it is BA and BC. For C, again, there are two members. It is CB and CD. And for D, there is only one member, DC. Okay. So what are the distribution factors? For AB, there is no distribution factor. For joint B, BA member, tell me the distribution factor. It is 0.55. And for BC, it is 0.45. Correct now? For BC, it is 0.52. And CD, it is 0.48. Okay. So these are the distribution factors. I have made a block over here because we will require these values continuously. As we go on writing in the table, we should keep in mind what are these distribution factors always. So tell me now the fixed end moments. For AB, it is minus
17.25.
17.25. For BA, it is plus 17.25. For BC,
Minus 35.42.
this is plus 35.42. For CD
33.33.
and DC, it is 33.33 again, but positive. Okay. Now the next step, if you consider the diagram of the beam, at the end A and at end B, there is a simple support. And at simple support, the moment is to be 0, right? So as we have calculated here the fixed end moment at these simple supports A and D, we need to first release this moment. So the first step here, after writing the fixed end moment, is we have to release the moment. Okay, so release, write down release here. So the moment is minus 17.25. If I want to make it 0, I have to apply equal and opposite moment. So I will write down plus 17.25 here. Similarly, at the D joint, there is a positive moment, 33.33. If I want to release this, release means to make it 0, I have to apply equal and opposite moment. So minus 33.33 will be there. Okay, and when I apply the moment will be carry forward to the next joint. Okay, some part of this moment will get carry forward or carry over to the next joint. So it is always carried over with a value of half, because the next joint is a continuous joint or intermediate joint, which is considered as a fixed support. So the carryover factor from this moment to the next will be half of this value. So tell me, what is the half of 17.25?
8.625.
8.625. Similarly, at the joint D, I have to carry over the moment from this to the next joint. So C joint is intermediate, so half of this value will get carry over. So what is the value?
16.665.
So 16.67 I will take. Okay, so this is a carryover step. Now, Write down the total moments here again. Total is 0 here because we have released this moment. Find out the total of these two values, 17.25 plus 8.625. What is the value?
25.875.
875. Similarly here, the value will come as it is 35.42. This is also 35.42. And find out this summation or total moment.
minus 50.
Minus 50.
Okay. So the next steps are at joint B. Let me draw these lines first. Make use of the scale now. At joint B and C, the moments, if you observe, the moment at in span BA is different and in span BC is different. So we have to find out the net moment acting at this joint. Okay. So what is the net moment of these two moments? That is 25.875 minus 35.42. What is the net moment?
Minus 9.545.
Okay, so I will write down here minus
545.
9.55. Let us see. Minus 9.55. So this is a net moment acting at this joint. Now I have to balance this moment by applying a equal and opposite moment. So I have to apply plus 9.55 moment here to balance this total moment. Okay. So now when we apply a balancing, when we do the balancing of by applying the 9.55 moment, it will get distributed to the two members at this joint with the distribution factor of 0.55 for BA and 0.45 for BC. Okay, so the moment will get distributed with 0.55 for BA. So it will be plus 9.55 into 0.55. What is the value? I will simply write down here. This is multiplied by 0.55. So what is the value?
5.25.
5.25. So this value will be 5.25 and it is positive. Similarly, for BC, it will be 9.55 into 0.45. What is the value?
4.29.
This is positive. 4.30.
23. 4.30. 30 करा.
30. बर. So this is 4.30. Okay. Similarly, now come to the next joint, that is joint C. Again, there are two different movements. So find out the net effect. 35.42 minus 50. What is the net
Minus
moment here?
14.58.
Minus 14.58.
58.
So I have again. Is it correct?
Yes, ma'am.
14.58. Okay. So I have to balance this moment by applying equal and opposite moment. So I have to apply a positive moment of 14.58 with the distribution factors of 0.52 for CB and 0.48 for CD. Okay. So multiplied by 0.52. Tell me the value.
7.58.
7.5.
5,
8.
8. So this is 7.58 and here this is 14.58 into 0.48. So 14.50
7.
again 7. All right. Okay, I will erase all this now. This is very tedious now. Now, what is the next step? This step is actually balancing step. So it is called as balance. This is balancing of moments. So after balancing, the next step is carryover. So carryover of these movements will be there. Now the movement from B to A will not get carryover because A is having a simple support. So carryover will happen with between B and C only. Okay, so I have to carry over this moment with a half value to C. Similarly, carry over this moment with a half value to B. So tell me half of 4.3.
2.15.
2.15. And half of this
3.79.
3.79. Okay, this is the carryover. Again, now I have to do the balancing step. So again, balance the net moment acting at this joint is 3.79. So I have to apply equal and opposite. So minus 3.79 multiplied by distribution factor of BC 0.55 and for CB it is 0.45. So do the calculation and tell me this value will be negative now. Why there is a difference in calculation, my calculation and your calculation? Let me check the formula again. You're doing the calculation now? Students.
Yes, ma'am. Yes, ma'am.
Hmm. You have to do this, you have to repeat these steps continuously till you get the equal moments here. If you consider these, the 5.25 and 4.30, there is a difference between the two values. So you have to keep repeating the steps of balancing and carryover till you get approximately equal moment on both the sides of the joint. Okay. So just keep on doing this and tell me what the value you are getting.
Ma'am,
Hmm?
I've got
Yes.
at AB span 0, at BA 29.28, at BC minus 29.28, at CB
Wait.
43.6.
Wait. Tell me again. Yes. This step you are telling me, or all further steps you have done?
Yes, ma'am, all further steps.
So total moment you are telling me, right?
Yes, ma'am.
Total moment or final moments you are
Final
telling
moments,
me?
ma'am. Yes, ma'am, final moments.
After adding all the moments.
Yes, ma'am.
That is from this step. After releasing from this step, you kept on doing this balancing carry over step, and then final addition of all this. You are telling me
Yes,
that,
ma'am.
right? Huh.
Yes,
So
ma'am.
I will
Fine.
have to
Same,
write down
similar.
here end moments, right? You are telling me end moments.
Yes.
So I will write down end moments. So yes, this will
At
be
AB, yes, 0,
hmm,
29.28, positive,
okay.
negative 29.28,
Hmm,
then positive 43.6,
okay.
negative 43.6,
And this
0,
is 0.
0.
So this is my MAB, this is MBA, this is MBC, and this is MCB and MCD, and this is MDC. Okay. All are getting the same answer, students? All other students are getting the same answer, or is there any difference? कोणा झालंच नाही का बाकीच्यांचं कॅल्क्युलेशन? Students? Yes, who was telling me from girls? Akshata or Arti? Who was talking with me? Students? All are getting the same answer? थांबूया का आपण आज? काय बोलायची इच्छा नसेल तुम्हाला तर? जितकं स्लो जाऊ आपण तितकं पुढे कॅल्क्युलेशन म्हणजे नंबर ऑफ लेक्चर्स वाढतील बरं का? If you give less response, I will stop now the lecture. एक्स्ट्रा लेक्चर्सला मग तयार राहा तुम्ही.
मॅम हेच येतात
Yes.
का कंटिन्यू?
हा?
मॅम करूयात पुढे कंटिन्यू याच्यात.
करेक्ट येतात व्हॅल्यूज?
आमचे अजून आले नाहीये, आपण याच्यावरती कंटिन्यू करूयात.
बर, ठीक आहे. All right. So just what is the time? Oh, it's 12:40. I need to stop now. Okay. We will draw simply the bending moment diagram here, and then we will stop. The further steps we will do in the next lecture. So let us draw the bending moment diagram. So all these are my end moments, whatever I have calculated here. So I will draw the bending moment diagram here. A, B, C, and D. Okay. Now, due to the external load, whatever is acting on the beam, due to this loading, the moments, whatever we calculate, the maximum moment for span A, B, B, C, and C, D, these are the free moments. Okay. So how these are calculated? Simply by considering this as a simply supported beam subjected to UDL, free moment will be WL square by 8. Okay, so tell me that value, WL square by 8, and that bending moment diagram will be a parabolic value. So what is the WL square by 8 value? Omkar?
25.875.
25.87. Okay. So for next span, for span BC, again WL square by 8. What is the value?
53.13.
Okay. So this is 53.13. And for CD,
50.
50.
50. Okay, so these are the free moments. Now I will plot end moments. So for joint B, the end moment is 29.28. So it will be somewhere here, very small value, 29 point. So I have to simply join these two lines. Okay, this is 29.28. So I will write down here 29.28. The next is 43.6. So somewhere here. So this I have to join here. 43.6. And then finally I will join this here. Okay. So my bending moment, this is positive, this is negative, this is positive, this is negative, this is positive. So this is my bending moment diagram. Okay. Now the next step, we will require shear force diagram also. So for that, we have to consider each span of the entire beam separately, find out the reactions. What is the reaction at A, B, C, D for the continuous beam, find out the shear forces, and then we will plot the shear force diagram for the entire beam. Afterwards, we will calculate the moments. Now the moments will be the span moments as well as the support moments. We need to calculate it separately. And then further steps is calculation of moment carrying capacity and area of the steel required for the beam. So this is a lengthy process. Design of continuous beam is a lengthy process. So we'll stop today here, and in the next lecture we will consider the remaining part of the beam or the design. Okay, so let us consider now the attendance. Attendance is very poor today. What happened?